Welcome, students. Today's lecture is a little bit on lesson 18 in the book. I did a Zoom meeting on this the other day, and the most important part about this lesson was about the dissociation of water and acids and bases. And I'm going to teach you about that dissociation today, that breakup. And I put a video in the homework link for you to watch about strong versus weak acids and strong versus weak bases. And in this lecture, I also talked about the difference between concentrated and dilute. Concentrated meaning the acid or base is dissolved in very little water, and dilute means it's dissolved in a lot of water. So if it's a concentrated acid, the molarity or concentration is high, and if you have a dilute acid or base, the molarity or concentration is very low. So the main focus of this lesson is about pH and the relationship between H plus, OH minus, and pH. So before we totally dig into this, I want to remind you of the pH scale. The pH scale has a low pH for things that are acidic and a high pH for things that are basic. But the scale is also a relationship of the H plus and OH minus concentration. So I'll show you a couple other scales that I found on the internet. Here's one right here. It shows the pH scale, and it says acidic this way and caustic this way. So caustic is another name for base. And neutral, of course, is right in the middle. If you have an acidic solution, you have a lot of H plus. If you have a caustic or basic solution, you have a lot of OH minus. If you're neutral, you have equal amounts of H plus and OH minus. If you're a pH around 5 or 6, so you're just slightly acidic, you have some H plus, but not as much as you have over here. And if you're at a pH of around 8 or 9, you have some OH minus, but not as much as you have here. And it turns out that even in an acidic solution, you have a little bit of OH. So I'll draw a small OH here. And in a slightly basic solution, you have a little bit of H plus. And in a really basic solution, you still have some H plus, but it's so small, it's negligible. And likewise, in an acidic solution, you still have a little bit of OH minus, but it's so small, we can say it's negligible. We don't even worry about it. Okay, so really, you have high H plus, low H minus, and over here you have high OH minus and low H plus. Here's another picture I found on the internet, and here they use the word alkaline to describe bases. So an alkaline solution is a basic solution. So acidic, there's really only one name for that, but for basic, we can say alkaline, we can say caustic, or again, we can say base. So the focus of this lecture then is going to be about calculations involving the relationship between pH and the molar concentration of H plus and OH minus. Keep in mind that pure water has both H plus ions and OH minus ions. Here's why. Water molecules are polar and they tend to tug and pull on each other, sometimes tearing each other apart. So let me draw that. Here is a water molecule that has moved its negative oxygen side toward this water molecule. Remember in a water molecule you have a slightly polar, remember that little symbol, slightly positive, and a slightly negative side. So slightly positive and slightly negative. Remember the water bent around the charged wand in that one experiment we did? Okay, so it's polar. Well, in this one right here, I'm going to show a new bond forming because the oxygen side of one water molecule, this one, is grabbing on to this positive hydrogen ion, and it's going to tear it apart. And when it does that, it's going to leave behind the electron in that electron pair. Remember, there was a pair of electrons being shared here, one from the hydrogen, one from the oxygen. And that electron is going to get left behind over here. So we end up with H3O plus, because just the proton was captured by this water molecule, and the electrons are left behind here. So here we get OH minus. OH minus, because the electron was left behind, so it takes on that negative charge. So keep in mind that this doesn't happen very often. If you have millions and millions of water molecules, only a few get broken apart. But every time it happens, you get one H3O plus for every one OH minus. So here's another H3O plus, and here's another OH minus. So it's 1 for 1. So in neutral water, we say that neutral water, the H plus concentration times the OH minus concentration, they're both very low. They always multiply out to 1 times 10 to the negative 14. That is, the concentration is 1 times 10 to the negative 7 molar. That's what the brackets mean. These brackets here mean molar concentration. So the molar concentration, that is the moles per liter, is 1 times 10 to the negative 7 hydrogen ions and 1 times 10 to the negative 7 hydroxide ions. Now that's a very low amount. Think about it. 1 times 10 to the negative 7 is 0.00000. Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's 1 times 10 to the negative 7. That's a very low concentration, 0.000001 molar. That's really low concentration. So in pure water, there's hardly any ions. There's hardly any hydroxide or hydrogen ions. Keep in mind, sometimes we just call it H+. But in reality, there's at least one other water molecule attached to it. So some people write this as H3O+, and sometimes people just write it as H+. That is, a water molecule, HOH, breaks apart into H+ plus OH minus. So a water molecule breaks apart. And again, usually that H+ is attached to at least one other water molecule. Sometimes more than one is attached to it. Okay? So we can call it H+ or OH minus. And the concentration is very low. So there's very few ions. And that explains, you might remember when I put the light bulbs in the different solutions, like the salt solutions and the acid solutions, that those conducted electricity, but water itself, pure water, was a poor conductor of electricity because there are so few ions in pure water. Only 1 times 10 to the negative 7 hydrogen and 1 times 10 to the negative 7 hydroxide. Let's see. Okay. So how about water molecules and acids and bases? Well, water molecules tear apart acids and bases too. And we say that they cause the acid and base molecules to dissociate. So that was a word in lesson 18. Dissociate, to break apart. So let's look at this sample of water that has some hydrochloric acid and some hydrofluoric acid. The hydrochloric acid is a strong acid. It completely dissociates when you put it in water. It completely breaks apart. Every molecule that you can get to dissolve will break apart. And here, every molecule of hydrofluoric acid that you could get to dissolve, well, not all of them will break apart, only a few, because they only partially dissociate. Now, there is a limit to how many molecules you can get to dissolve, but once you've got them to dissolve, all the hydrochloric acids will break apart, and only a few of these will. So we might get something that looks like this. Let's see. Here, this water molecule will grab onto that hydrogen, making H3O+. And what's left behind? The Cl-. Now the Cl minus could be attached over here to that water. That does happen. The chloride ions are surrounded by water, but we just write it as Cl minus. And here, this one will grab on here to make an H3O plus. And this one, maybe this one here, will grab on to make, let's see, this one right here, grab on to make an H3O plus. And this one right here will grab on to make an H3O plus. And let's see, I got one more. I got to grab on one more spot. And that one there will grab on to make an H3O plus. Now over here, of these 5 hydrofluoric acid molecules, maybe only one of those gets torn apart or dissociated. So that one is going to get torn apart, but the others will stay the way they are as HF molecules. It's true that the water will be oriented around them because this is a slightly negative side and this is a slightly positive side. So the water molecules will certainly orient properly around them, but the water molecules will not tear them apart, as has happened here. Only one in many will be torn apart. So that's the difference between a strong acid and a weak acid. Complete dissociation, only a slight dissociation. So again, this goes back to lesson 18. And again, if you're a little unsure, there's a couple videos I've put in that you could watch. Okay, let's move on to this page here. What would happen to the balance of H plus and OH minus if you added an acid to the solution? Okay, so let's add an acid to this solution. So here's, again, here's water, and only a few of them have broken apart. Most of the water molecules are not broken apart. So we've got a few H3O pluses and a few OH minuses, equal amounts in pure water. But now I'm going to add an acid. So in this case, I'm going to add, let's try another color. How about, I'm running out of colors. I'll just throw in a red one here. Okay. How about if I add an HCl right here? Here's an HCl, hydrochloric acid molecule. When I do that, the hydrochloric acid sometimes will be torn apart by water, but sometimes it'll grab onto the OH that's already in solution. And what do we get when it grabs onto an OH? We get an H2O. So this hydrochloric acid molecule actually caused the OH minus to go down. When we add acid to water, OH minus goes down. But sometimes when we add acid to water, it causes the H3O plus to go up because, again, the water's going to tear that away. So the H plus goes up while the OH minus goes down. How about if we add a base to water? Well, if we add a base, like here I'm going to add a sodium hydroxide. I'm going to add a sodium NaOH. If I add an NaOH, as it breaks apart, sometimes it will grab on to the H plus from an H3O plus. And that will leave a water behind, and it will make another water molecule. So this causes the H plus or H3O plus concentration to go down when we add a base. And sometimes when we add a base, if we put it in water, I'll put one up here. Sometimes it breaks apart and causes the OH minus to go up. Now you might be saying, well, Mr. Wood, it looks like that oxygen could grab on there. It could grab on there just like that. But then that leaves an OH behind here. So there's this constant battle going on in solution where H pluses are grabbing onto water, or OH minuses are grabbing onto water and tearing things apart. But you get the idea that when we add an acid to water, the OH goes down and the H plus goes up. And when we add a base to water, the H3O plus or H plus goes down and the OH goes up. Okay? That's what I had written there, but I didn't want to redraw them all. So really I kind of did them both right there in that one picture. If we add an acid or a base, we cause the OH and the H plus to change depending on what we add. And I want to show you a picture here. Now, it's going to be hard for you to see this whole thing. Let's see if I can quickly zoom out here. Sorry, my technology is not so good. I can't get my document camera to work. Let's see if I lift that up a bit. There we go. Okay, now you can see this whole document here. Okay. So this is a relationship between pH and the molar concentration of H plus and OH minus. If the H plus concentration is very high, as let's see, as I explained, which page was that? Well, I was telling you here that that in neutral water you have the same amount of each, 1 times 10 to the negative 7, but as we add acid, H plus goes up, and as we add hydroxide, OH minus goes down. But there's a little bit of each. Let's see, is this page right here. So here, if you have an acid, you have a lot of H plus and a tiny bit of OH minus. If you have a base, you have a lot of OH plus or OH minus and a little tiny bit of H plus, and neutral is equal. Well, that's what this page is showing right here. That's what this page is showing. It's showing the concentrations. So 1 times 10 to the negative 0, 10 to the, not negative 0, but 1 times 10 to the 0. Keep in mind 10 to the 0 is equal to 1. So really that's just 1 times 1, or 1. 1 times 10 to the negative 1 molar concentration of H plus, or 0.1, is a pH of 1. And a 0.01 molar concentration, which is 1 times 10 to the negative 2, is a pH of 2, and so on. Over here, if you have a solution that has a 1 molarity H plus, this is the concentration of the OH minus, really, really small, 1 times 10 to the negative 14. If you're at 7, pH of 7, then the solution is neutral and you have the same amount of each, 1 times 10 to the negative 7. And if you have a very basic solution or very alkaline or caustic solution, you have a 1 molarity OH minus and a really low concentration of H plus. But the whole idea is that as one goes up, the other goes down. You can see as one goes up, the other goes down. So this is very acidic. And this, going this way, is very basic. And right in the middle, of course, is neutral. Okay? All right. So now what we're going to do is talk about some math problems that have to do with pH and H plus and OH minus. So pH is a simple scale we use because using numbers like 10 to the negative 7th, those are really kind of hard numbers for people to recognize. If you want common people to understand pH, then you got to give them some easy numbers, like a scale of 1 through 14. So scientists have created this scale, again, in part to help people understand easily the difference between an acid and a base. A low pH acidic, a high pH basic. But where do those numbers come from? Well, they come from what's called a log base 10 scale. And I'm not going to say a whole lot about that, and you've probably studied it in math. In a log base 10 scale, a change of 10 times the concentration results in a change of just 1 pH in the scale. So do you see how going from here to here, this concentration is 1/10 of this one. So the pH changed by 1. This concentration is 1/100th of this one. So the pH changed by 2. Okay, likewise, when this changed by a factor of 100, so did this one here. From here to here is changing by a factor of 100. So a change in concentration by a factor of 10 is a change of pH of 1. A change in a change in concentration of 1,000, going, say, from here to here, gives you 3 changes of pH, from 1 to 4. So we change 1, 2, 3 changes of pH. That would be 10 times another factor of 10 times another factor of 10. That is a factor of 1,000. Okay? All right. So the 3 equations that we're going to use are these 3 right here. And they're going to answer all the questions you need, except some of you, I'm going to show you one little extra equation at the end. Is sort of a shortcut. But these 3 right here are all you're going to need to know for this class. Okay? The extra one is something my AP students learn. All right. So keep in mind that H plus times OH always equals 1 times 10 to the negative 14, right? As one goes up, the other goes down. What's this number times this number? 1 times 10 to the negative 14. What's this number times this number? 1 times 10 to the negative 14. If we multiply them out, they always multiply out to 1 times 10 to the negative 14. Because as H plus concentration goes up, OH minus concentration is going down. Okay, so keep in mind, those two always multiply out to 1 times 10 to the negative 14. Okay, so let's do a simple problem here. If A times B equals C, for instance, 3 times, got the wrong number there, 3 times 4 equals 12. What is this number if we don't know it? Wouldn't we do, to find that number if we didn't know it, wouldn't we move this underneath over here? That is 12 divided by 3 would be this number. Okay, well, we can do the same thing with this equation. If we know the H plus, but we don't know the OH minus, but we do know that they always multiply out to 1 times 10 to the negative 14. And we'll say that this is the green. And we want to find that green. We want to find the OH minus. Then really all we have to do is OH minus equals 1 times 10 to the negative 14 divided by the H plus concentration. So let's try that with this problem right here. A solution has an H plus concentration of 0.00042. What's the OH concentration? Well, keep in mind that this number can also be written this way. Watch, 1, 2, 3, 4. 4.2 times 10 to the negative 4. So I'm going to show you in a calculator that we could really solve the problem using either one of those numbers. So if we want to know the OH concentration, then really we're going to do OH equals 1 times 10 to the negative 14 divided by 0.00042. Or we could do it 1 times 10 to the negative 14 divided by 4.2 times 10 to the negative 4. We can do it either way. So now I want to show you how to use your calculator, and I'm also going to post a video in the homework link that is specifically to remind you how to use this calculator. And you could just rewind this video and watch mine, but just in case you want to just see it from somebody else, you can. Okay, so I'm going to turn that on. And anytime I'm using scientific notation, I'm going to put parentheses around the scientific notation. Okay, so I'm going to type in a parenthesis, and then I'm going to type in 1. And now I'm going to show you a little different way than I showed you before. In class, we did some scientific notation before, and I showed you a little bit different way. What I'm going to show you now is actually a little bit easier. So this EE button right here, or sometimes it'll say EXP, means exponent. And of course, that's for this key right here. And since it's the blue one, I have to hit the second button. So I want to do 1 times 10 to the negative 14. So what I'm about to do is the times 10 to the button. That's what this is, the times 10 to the, times 10 to the, and then whatever. I'm going to type that number in. So I'm going to hit second, EE. And now I'm going to type in the negative. So I'm going to hit the negative button. I'll have to move the calculator up so you can see it. The negative, and then 14. And there we go. Now you can see it there. Negative 14. And now I'm going to close my parenthesis. And then I'm going to hit divide. And now I'm going to divide by 0.00042 and hit enter. And that gives me 2.3 times 10 to the negative 11. Okay. So I'll write that answer here. OH concentration equals 2.38. I'll round it off there, times 10 to the negative 11. So there's my answer. Okay, now I'm going to show you using this one here. Okay, so I'll clear that. Okay, once again, I'm going to type in 1. Oops, and I got to use my parenthesis. Okay, parenthesis 1. Second, EE to give me the times 10 to the, and now the negative button down below, 14, close parenthesis, divide by, use my parenthesis again, make sure you put parentheses around them. Sorry, my calculator's in the way. Divide by, let's see, parenthesis, 4.2, second, EE, that's the times 10 to the, and now a negative 4, close parenthesis, enter, and I get the same answer, 2.38 times 10 to the negative 11. And keep in mind, that's molar, the molarity of the hydroxide. So that's what I just figured out, the molarity of the hydroxide. Okay, so keep in mind, if you know one, you can find the other. We could do the reverse, so that's what this problem is. A solution has an OH concentration of 2.7 times 10 to the negative 5. What is the H plus concentration? So here I'm going to do, let's see, I want to know the H plus this time. So the H plus will equal 1 times 10 to the negative 14 divided by the OH minus, 2.7 times 10 to the negative 5. And again, I need to use parenthesis. Okay, so I'm going to type in 1. Oops, nope, back up. Got to use the parenthesis. Okay, I'm going to type in 1 times 10 to the negative 14, close parenthesis, divided by, use my parenthesis, 2.7 times 10 to the negative 5, close parenthesis, and hit enter. And I get my answer, 3.7 times 10 to the negative 10. Okay. All right. So now let's do the next problem. The next problem is, what do you do if you want to find the the pH? Now we want to find the pH, and we're given the H plus concentration. So we're going to use this equation right here, pH equals negative log of H plus. Okay, so I'm going to do pH equals negative log of H plus. So I'm going to type in, the negative button first, negative. Then I'm going to hit the log button. And then I'm going to use my parenthesis because I'm going to put scientific notation in there. I got to use the parenthesis. 7.4, hit my second button, E, that gives me the E, and now that's my times 10 to the, and now I put in my negative 11, close parenthesis, enter, and I get 10.1, I'm going to round it up to 0.13 molar. If you're wondering about rounding, just give me one decimal if you would, but technically what I'm supposed to do is, since there are two numbers in this H plus concentration, I'm supposed to extend the answer two places past the decimal. So that's the rule for how you round off here, but that's something I teach in AP, but just give me one decimal if you would in your answer. So in this case, 10.1 would be fine, or 10.13. If you want to write the whole thing, fine, but give me one decimal. Okay, so that's finding the pH from the H plus concentration. Okay, now we're going to do the pH of this hydrochloric acid solution. So keep in mind, hydrochloric acid is a strong acid, so the concentration of this acid is also the concentration of the H plus, because all of the HCl will break apart into H plus Cl minus. And again, keep in mind, it's attached to a water molecule, so sometimes people call it H3O plus. But we can just simplify it this way. So we get an H plus concentration for, we get one H plus for every molecule that we put in water. So if the concentration of the HCl is 5.3 times 10 to the negative 4, then the H plus concentration is also equal to 5.3 times 10 to the negative 4. All right? So now all I have to do is take the negative log of 5.3 times 10 to the negative 4. And so in my calculator, I'm going to type, once again, my negative, then the log button, and that gives me my parenthesis. That's kind of nice. Second, got to back up, delete. Okay, negative log 5.3, and now times 10 to the negative 4, close parenthesis, enter. And I get 3.27. So that's my answer. 3.27 is the pH. In this case, again, I had 2 decimals here, so I have to extend 2 decimals past I have to expend 2 digits past the decimal. Technically, I guess, because that's a 5, this should really be 2.8. But I'm not going to ever grade you on how you rounded something off. So there you go, 3.28. The next problem, what is the pH of a soap solution with an OH concentration of 3.22 times 10 to the negative 5? So soap is basic. Let's see here. I had one of those scales I had. They'll go. Oh yeah. Here's another scale here. You can see detergents, ammonia, household bleach. They're very basic. So a soap is going to be basic. We should get some answer. We should get some pH in this range here, because soaps are basic. Citrus fruits are acidic, so if this was a citrus fruit problem, well, we should get a low pH. So let's see here. We're given the OH concentration of 3.22 times 10 to the negative 5, but remember, pH equals negative log of the H plus concentration, and we don't have the H plus, we have the OH. So what are we going to do? We're going to use this equation here. We're going to find the H plus from the OH concentration. So H plus equals 1 times 10 to the negative 14 divided by 3.22 times 10 to the negative 5. Don't forget to use parentheses. So on my calculator, I'm going to do parenthesis 1 exponent negative 14 close parenthesis divided by parenthesis 3.22. Give me my exponent, negative 5, close parenthesis, equals 3.11 is the H plus. 3.11 times 10 to the negative 10. So that's the H plus concentration. Are you starting to notice that this negative 10, the pH should then be around somewhere near 10, like 9 point something or 10 point something, somewhere near 10, okay? So I'm going to now do my pH, which is negative log, and it starts my parentheses, so I just type in my 3.11, give me my exponent, negative 10, close parenthesis, enter, and I get 9.5. So pH was equal to negative log of 3.11 times 10 to the negative 10, which equaled 9.51. We'll round that off. Okay, so there you go. My prediction was that, hey, it's got to be somewhere near 10. That gives you a quick estimate of what you should get for an answer. Let's look back at some of these. Look here, 5.3 times 10 to the negative 4. Well, then the pH should be around 4. Oh, there you go, 3.28. Let's look at the previous problem. Right here, the H plus concentration times 10 to the negative 11. There you go. We have an answer near 11. Okay. Now, for you fancy pants math people, check this out. Keep in mind, H plus times OH equals 1 times 10 to the negative 14. That is, in pure water, those two equal 1 times 10 to the negative 14. If you take the pH of 1 times 10 to the negative 7, you get 7. If you take what's called the POH, the negative log of the OH, you also get 7. So in this case, 7 plus 7 equals 14. That is, pH plus POH equals 14. If that's true, then we could also find the pH by subtracting this from the other side. So 14 minus POH gives pH. So I'm going to do 14 minus POH, which is the negative log of the OH concentration, which up here, our previous problem, 3.22 times 10 to the negative 5. So 14 minus POH, which is 14 minus the negative log of 3.22 times 10 to the negative 5. Now keep in mind, you're subtracting a subtraction, which is really an addition. So we can simplify it to 14 plus the log of 3.22 times 10 to the negative 5. So I'm going to type in 14 plus, and now I'm going to put in parentheses, log, and now I'm going to do 3.22 second, my exponent negative 5, close my parenthesis, and now I'm going to close the parenthesis one more time. Let's see if this is going to work here. Gives me my answer. What do you know? 9.51. There we go. So that's our answer. All right. So kind of a fancy pants way to do that. If you'd like, you can just remember to do 14 minus POH, which is 14 minus the negative log of the OH concentration. And so just do two problems. Do this problem first, and then subtract that answer from 14. Because remember, doing that actually gives you a positive answer, and you'll get your correct answer. Now, one more here. What is the pH of an 8.6 times 10 to the negative 3 molar solution of H2SO4? Now, this one's a little bit tricky. Just one little trick to it. Keep in mind H2SO4. You learned in lesson 18 that it's this hydrogen out in front that dissociates. In this case, two of them break apart. So really, the concentration of the hydrogen ion is twice the concentration of the sulfuric acid, because two are released from every molecule. So there's a couple ways we can do this problem. We can do pH equals negative log of 8.6 times 10 to the negative 3. Remember, that's going to be in parentheses. And then multiply our answer by 2 when we're done. But I'm going to do it this way. I'm going to do pH equals negative log of 2 times 8.6 times 10 to the negative 3, close parenthesis and another parenthesis. You guys might like the first way better, but I'll be a little fancy here. So I'm going to do negative log, and then I'm going to hit, it gives me the parenthesis to start with, so I don't have to put in this parenthesis. 2 times, now I'm going to do a parenthesis, 8.6 exponent, negative 3, close the parenthesis, and then one more parenthesis, equals. And again, I get my answer, 1.76 times, just 1.76 is my pH. pH equals 1.76. If we did it the other way, we could just do, and again, you might like it this way better, we're going to do negative log, and then 8.6 exponent, close the parenthesis, enter, whoops, what did I do wrong? Let's try again. Negative log, I see. Let's try it again. Negative log 8.6 times 10 to the negative 3, close parenthesis, equals 2.06. And something is not quite right here. And I typed something in wrong here. 8.6 times 10 to the negative 3. This is probably the better way to do it. And then, no, I can't do it that way. No, I can't double that. Sorry, I can't double that answer. I'm sorry, you can't just take your pH and multiply it by 2 then. You can't do that. You definitely have to do it the way I showed you first, and that is to multiply the 2 times the 8.6 times 10 to the negative 3 and take the log of that, the negative log of that. So really what I should be doing is I could do 2 times 8.6 second negative 3 answer, and that gives me 0.0172. Okay, and now I'm going to do negative log of, in this case I'll just type it in this way instead of doing 1 times 10 to the negative, or 1.72 times 10 to the negative 2. I'll just type in that number the way it is, 0.0172, close parenthesis, enter. And again, I get 1.76. So, okay, sorry, you can't just find your answer and multiply by 2. You actually have to take the negative log of twice this value. So either this way or the way I showed you here will get you the answer. So there you go. That's how you do lesson 19.